Welcome back to Whispering Universes, where tonight we venture into the most desolate regions imaginable. Not the depths of a black hole, not the frozen outer reaches of some distant solar system, but something far stranger and more fundamental to the architecture of everything we see. Tonight, we explore the cosmic voids, the vast empty spaces between galaxies where matter becomes so sparse that you could travel for hundreds of millions of light years without encountering a single substantial galaxy. Imagine, for a moment, that you find yourself floating in the center of one of these regions. You look around in every direction, and there is almost nothing. No bright galaxies nearby, no glowing nebula, no clusters of stars to guide your eye. In the far distance, impossibly far, you might see a faint smudge of light marking the edge of this emptiness, where the cosmic web begins again and galaxies cluster in their billions. But here, in the heart of a cosmic void, you float in a darkness more complete than almost anywhere else in the observable universe. The paradox is this: these voids are not merely gaps in the distribution of matter. They are structures in their own right, the largest structures we can identify in the cosmos. They shape the universe as profoundly as the galaxies and clusters do. They occupy the majority of the universe's volume. And yet, when we speak of cosmic architecture, we tend to focus on where matter gathers, on galaxies, stars, planets, the bright and obvious things. We overlook the negative space, the emptiness that gives shape and meaning to everything else. But emptiness, as we'll discover tonight, is never truly empty. The cosmic voids contain hints of dark matter, diffuse gases at temperatures of millions of degrees, magnetic fields stretching across incomprehensible distances, and radiation from the beginning of time passing through unimpeded. They are laboratories for testing our deepest theories about dark energy and the fate of the universe. They raise profound questions about what it would mean to be isolated from the rest of existence, to live in a void galaxy so distant from others that the universe would seem a fundamentally different place. The story of the cosmic voids is the story of how we discovered that the universe is not a smooth distribution of galaxies scattered randomly through space, but rather an intricate foam-like structure, a cosmic web of filaments, walls, and nodes, all separated by these enormous empty regions. It is a story of patient observation, of astronomers spending decades mapping the positions of millions of galaxies and discovering patterns that revealed something unexpected about the nature of cosmic structure itself. Throughout human history, we have been fascinated by what fills space, by the matter and energy that make up stars and galaxies. But increasingly, cosmologists recognize that the spaces between are just as important. The voids contain more than 80% of the universe's volume. They expand faster than the average cosmic expansion. They grow over time, becoming emptier and more isolated as the universe ages. Understanding them means understanding the skeleton on which everything else hangs. As you settle in tonight, prepare for a journey unlike any we've taken before on Whispering Universes. We'll travel from the discovery of cosmic structure through the physics of void formation into the unexpected things that actually inhabit these supposedly empty regions, and finally to what the voids tell us about the ultimate nature and fate of the cosmos. We'll visit the most famous voids, from the Boötes void discovered in the 1980s to supervoids so large they seem to challenge our cosmological models. We'll contemplate what it would be like to cross one of these regions, to spend millions of years in transit through a realm where galaxies are rare and distant whispers of light. The voids invite us to think about absence, about the spaces between, about what it means for something not to be there. They remind us that structure emerges not just from where matter collects, but from where it doesn't. They show us that emptiness itself can be a thing worth studying, worth contemplating, worth understanding in its own right. So let us drift now toward the edges of the cosmic web, toward the boundaries where galaxies thin out and the great voids begin. Let us explore what it means for space to be truly empty, and discover that even in the deepest emptiness, there are secrets waiting to be understood. For most of the 20th century, astronomers assumed that galaxies were distributed more or less uniformly throughout space. Oh, they knew that galaxies clustered together. The fact that our own Milky Way belongs to a small group of galaxies, and that nearby space contains larger clusters like Virgo and Coma, had been established decades earlier. But the prevailing view held that at large enough scales, when you stepped back far enough, the universe would smooth out. The clusters would average away into a homogeneous distribution, with no particular structure on truly cosmic scales. This assumption was wrong, and discovering how wrong it was required a painstaking effort to map the three-dimensional positions of thousands, then millions of galaxies across vast reaches of space and time. The revolution began in the 1970s and 1980s, when astronomers like Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman conducted galaxy redshift surveys that revealed unexpected structure. By measuring not just the position of galaxies on the sky, but also their redshifts, which indicated their distances, these researchers could create three-dimensional maps of cosmic structure. And what they found was astonishing. Galaxies were not smoothly distributed. They traced out a pattern that resembled nothing so much as the structure of foam or soap bubbles. Galaxies congregated in filaments and sheets, forming walls and tendrils that stretched across hundreds of millions of light years. Where these filaments intersected, you'd find massive clusters containing thousands of galaxies. But between the filaments, there were enormous regions, voids, where galaxies became extraordinarily rare. In 1978, Estonian astronomers Jaan Einasto and Mihkel Joeveer were among the first to recognize this large-scale structure. Working at the Tartu Observatory, they analyzed the distribution of galaxies and proposed that the universe had a cellular structure, with galaxies concentrated in the walls of cells and large empty regions in the interiors. It was a radical suggestion that challenged the prevailing cosmological assumptions of the time. The evidence became undeniable as more extensive surveys were completed. The CFA Redshift Survey, conducted at the Harvard-Smithsonian Center for Astrophysics in the 1980s, produced a famous plot that astronomers still call the stick figure diagram. It showed galaxies arranged in thin sheets and filaments, with obvious voids between them. The pattern looked remarkably like a cross-section through foam, with bubble-like empty regions surrounded by thin walls of matter. This cosmic web structure emerges naturally from the initial conditions of the universe, combined with the action of gravity over billions of years. In the early universe, immediately after the Big Bang, matter was distributed almost uniformly, with only tiny density fluctuations, regions that were slightly more or less dense than average. These fluctuations, imprinted in the first instance of cosmic inflation, were the seeds from which all structure would eventually grow. Gravity amplifies these small differences. Regions that start slightly denser attract more matter, becoming denser still. Regions that start slightly less dense lose matter to their denser neighbors, becoming emptier. Over cosmic time, this process produces a hierarchy of structure. Small clumps merge into larger ones, which merge into larger ones still, while the underdense regions expand and become increasingly empty. The pattern that emerges is not random, but follows principles that physicists can describe mathematically. The cosmic web reflects the gravitational growth of structure from quantum fluctuations in the early universe. The filaments trace out the paths along which matter flows, channeling gas and dark matter from voids toward the densest regions. The voids themselves expand as matter evacuates them, pushed by their own internal gravity deficit and pulled by the gravitational attraction of surrounding overdense regions. Computer simulations of cosmic structure formation, which track the evolution of billions of particles representing dark matter and gas, reproduce the cosmic web pattern with remarkable accuracy. These simulations start with initial conditions that match what we observe in the cosmic microwave background, the afterglow of the Big Bang, and then let gravity work its way forward through cosmic time. Without fail, they produce a foamy structure of filaments, walls, and voids that closely resembles what we see in galaxy surveys. The cosmic web is thus not some accidental arrangement, but the inevitable result of how gravity sculpts the universe. The voids are as fundamental to this architecture as the filaments and clusters. They are the negative space that gives shape to the positive, the emptiness that makes structure visible. Understanding the cosmic web means understanding both where matter collects and where it doesn't, and recognizing that these two aspects of structure are inseparable, two sides of the same cosmic coin. As the 21st century progressed, and galaxy surveys expanded to include millions of objects, the cosmic web became even more apparent. Surveys like the Sloan Digital Sky Survey mapped vast volumes of space with unprecedented precision, revealing the full complexity of void structure. Not just simple bubbles, but hierarchies of voids within voids, tunnels and channels connecting different regions, and variations in void properties that hint at the underlying physics of cosmic evolution. The cosmic web that these surveys revealed extends as far as we can see in every direction. It is the fundamental architecture of the observable universe, a pattern of filaments and voids that governs where galaxies form, how they evolve, and ultimately how matter is distributed across the largest scales imaginable. How do you measure something that isn't there? How do you identify and characterize emptiness? These questions might sound philosophical, but for astronomers studying cosmic voids, they're eminently practical challenges that require sophisticated observational techniques and careful statistical analysis. The first step in studying voids is identifying them, which means conducting comprehensive surveys of galaxy positions. This requires large telescopes, sensitive detectors, and years of patient observation. Astronomers must measure the apparent brightness and color of millions of galaxies, then obtain spectra for as many as possible to determine their redshifts. The redshift, the degree to which light has been stretched to longer wavelengths by cosmic expansion, directly indicates how far away each galaxy lies. With positions on the sky and distances in hand, astronomers can construct three-dimensional maps of galaxy distribution. These maps reveal the cosmic web structure we discussed in the previous chapter. But within these maps, how do you formally define a void? Where exactly does a void begin and end? How empty must a region be to count as a void rather than simply an underdense region? Different researchers have developed various void-finding algorithms, each with its own definition and criteria. One common approach searches for spherical regions that contain significantly fewer galaxies than average. The algorithm might start by placing test spheres of various sizes throughout the survey volume and calculating the galaxy density within each. Regions where the density falls below some threshold, often defined as less than 20% of the average cosmic density, are identified as potential voids. Other algorithms take different approaches. Some identify voids by looking for regions bounded by walls of galaxies, essentially finding the soap bubble structure directly. Others use the distribution of galaxy separations, identifying voids as regions where typical distances between galaxies are much larger than average. Still others employ sophisticated mathematical techniques from topology and geometry, treating the galaxy distribution as a mathematical object and identifying voids as particular topological features. Each method has advantages and limitations. Spherical void finders are simple and intuitive, but may miss irregularly shaped voids. Watershed algorithms that trace walls can find complex shapes but may be sensitive to survey boundaries and incomplete data. The choice of method affects the void catalog you produce, how many voids you find, how big they are, and what properties they have. Once voids are identified, astronomers measure their properties. The most basic measurement is size, typically characterized by an effective radius, the radius of a sphere that would contain the same volume as the actual void. The smallest voids might be 30 or 40 million light-years across, while the largest known voids exceed 300 million light-years in diameter. For comparison, the distance from the Milky Way to the Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years. The largest voids could contain more than 100,000 Milky Way-Andromeda separations. Astronomers also measure void density contrast, how much emptier a void is compared to the average universe. Even the emptiest voids aren't completely devoid of matter. They might contain 10 to 20% of the average cosmic density, mostly in the form of dark matter and diffuse gas, with a handful of isolated dwarf galaxies scattered through the volume. The density contrast is typically expressed as delta, the fractional deviation from average. A region with delta equals negative 0.8 has 20% of the average density. The shapes of voids are quantified using ellipticity or other shape parameters. While early models often assumed spherical voids for simplicity, real voids are triaxial ellipsoids with varying degrees of elongation. Some voids are nearly spherical, while others are highly elongated, resembling cosmic tunnels or channels. The shape depends partly on the void's environment, whether it's surrounded by other voids or embedded in a region of more complex structure. Modern void catalogs contain thousands of voids identified in galaxy surveys. The Sloan Digital Sky Survey, which mapped more than 1 million galaxies, has enabled the identification of void catalogs containing more than ones and voids with well-measured properties. These catalogs are publicly available, allowing researchers worldwide to study void properties and test cosmological theories. The precision of void measurements depends critically on the quality of the underlying galaxy survey. Incomplete surveys that miss faint galaxies may identify apparent voids that are actually populated by galaxies too faint to detect. Survey boundaries can artificially truncate voids, making them appear smaller than they really are. Selection effects, biases in which galaxies are included in the survey, can systematically affect void properties. To address these challenges, astronomers use mock catalogs generated from simulations. By taking a simulated universe where the true matter distribution is known and creating a mock survey that mimics the selection effects and limitations of real observations, researchers can test their void-finding algorithms and understand how well they recover true void properties. This process of validation is essential for ensuring that the voids we identify in real data actually represent physical structures rather than artifacts of observational limitations. The ongoing efforts to measure and characterize voids have revealed that they form a well-defined population with predictable statistical properties. Voids follow a size distribution that peaks around 60 to 80 million light-years in diameter. Larger voids are rarer, following a power law distribution. The abundance of voids as a function of size provides a sensitive test of cosmological models, particularly those involving dark energy and modified gravity. Measuring nothing, it turns out, is a sophisticated science requiring the same level of precision and care as measuring anything else in the cosmos. The voids may be empty, but understanding that emptiness requires the full arsenal of modern observational astronomy. Numbers and statistics might seem dry, But when applied to cosmic voids, they reveal patterns that tell us something profound about the universe's structure and evolution. The way voids are distributed, their typical sizes, how many of them exist, and how these properties change with cosmic time. All of these statistical descriptions encode information about fundamental physics. Let us start with the most basic question: how much of the universe is void? The answer depends on precisely how you define void. But using typical definitions that identify regions with less than 20% of average cosmic density, voids occupy somewhere between 40 and 60% of the universe's volume. If you're willing to call any underdense region a void, even one with 50% of average density, then voids occupy 80% or more of cosmic volume. The exact fraction matters less than the general picture. Most of space is underdense, with matter concentrated in a relatively small volume within filaments, walls, and clusters. The size distribution of voids follows a pattern that cosmologists can describe mathematically. Small voids are more common than large voids, with the number of voids decreasing roughly as a power law as you move to larger sizes. A typical void catalogue from a modern survey might contain hundreds of voids in the 40 to 80 million light-year diameter range, dozens in the 80 to 150 million light-year range, and only a handful that exceed 200 million light-years. The largest voids identified in surveys are truly staggering in scale. The Boötes void, discovered in 1981 and sometimes called the Great Nothing, spans approximately 330 million light-years across. Within this vast region, astronomers found only about 60 galaxies where you might expect 2,000 if the region had average cosmic density. For decades, the Boötes void held the record as the largest known void. More recently, surveys have identified voids that rival or potentially exceed the Boötes void in size. The Giant Void in Cairns Venatici, the Capricornus Void, and several others discovered in Sloan Digital Sky Survey, data all measure between 200 and 350 million light-years across. The Eridanus Supervoid, which we'll discuss more in a later chapter, may be even larger, though its exact nature remains debated. These supergiant voids present interesting challenges for cosmological models. Standard theories of structure formation predict a maximum void size that depends on the age of the universe and the properties of dark energy. Voids can only grow so large in the time available since the Big Bang. Finding voids at or near this theoretical maximum provides a test of our cosmological assumptions. If we find voids significantly larger than predicted, it might indicate problems with standard cosmology or suggest new physics. Beyond size, astronomers study the shapes of voids and how they're distributed relative to each other. Voids aren't randomly scattered through space, but show correlations. They tend to cluster, with voids often found near other voids, separated by thin walls of galaxies. This void-void correlation is weaker than galaxy-galaxy correlation, but it's measurable and provides information about how structure evolved. The ellipticity distribution of voids, how elongated or spherical they are, also contains cosmological information. Simulations predict that voids should be more spherical in universes with certain properties and more elongated in others. The observed distribution of void shapes can thus constrain cosmological parameters like the dark energy equation of state or the nature of gravity on cosmic scales. Voids also display what cosmologists call hierarchical structure. Just as galaxies cluster into groups, groups into clusters, and clusters into superclusters, voids show a hierarchy of scales. Large voids contain smaller voids, which may contain even smaller voids. This voids within voids structure reflects the self-similar nature of gravitational structure formation. Analyzing this hierarchy, quantifying the typical scales at which voids nest within larger voids, tests our understanding of how cosmic structure grows over time. The abundance of voids changes with cosmic redshift, which means it changes as we look back in time to earlier epochs of the universe. In the distant past, when the universe was younger and denser, voids were smaller and less empty. As cosmic expansion proceeds and structure continues to evolve, voids grow larger and emptier. By studying how void abundance and properties change with redshift, astronomers can trace cosmic evolution and test models of how structure formation proceeds. One particularly interesting statistical measure is the void probability function, which describes the probability of placing a sphere of a given radius somewhere in the universe and finding it completely empty of galaxies. For small spheres, this probability is low. You'll almost certainly find at least one galaxy. As the sphere size increases, the probability of emptiness rises, reaching significant values for sphere radii of tens of millions of light-years. The exact form of this function depends on cosmological parameters and provides another avenue for testing theories. Voids also affect the statistical properties of galaxy distributions in ways that might not be immediately obvious. The presence of voids introduces what statisticians call non-Gaussian features into the cosmic structure. While the initial density fluctuations from inflation were nearly Gaussian, following a simple bell curve distribution, the gravitational growth of structure introduces deviations from this simple pattern. Voids contribute to these deviations, and measuring them helps us understand the early universe. All of these statistics, size distributions, shape distributions, correlations, hierarchies, and evolution, combine to create a comprehensive picture of void properties. Cosmologists compare these observed statistics to predictions from simulations based on different cosmological models. The models that best reproduce the observed void statistics are the ones that most likely describe our actual universe. The statistics of emptiness, then, are anything but empty themselves. They're rich with information, encoding the history of cosmic structure formation, the properties of dark energy, perhaps even hints about the nature of gravity itself. The voids may be vast and underpopulated, but their statistical fingerprints speak volumes about the cosmos. Understanding how cosmic voids form requires us to trace the evolution of the universe from its earliest moments through billions of years of cosmic time. The story of void formation is intimately connected to the story of all cosmic structure. Galaxies, clusters, filaments, and walls all emerge from the same process that creates voids. They are different manifestations of the same gravitational symphony. In the beginning, within the first fraction of a second after the Big Bang, a process called cosmic inflation stretched a tiny patch of space into a region vastly larger than the observable universe today. This rapid expansion amplified quantum fluctuations, tiny random variations in energy density at subatomic scales, into macroscopic variations that would eventually become the seeds of all cosmic structure. These primordial density fluctuations were incredibly small, variations of only about 1 part in 100,000, but they were all that was needed. By the time the universe was about 380,000 years old, it had cooled enough for electrons and protons to combine into neutral hydrogen atoms. This epoch, called recombination, marks the moment when the universe became transparent to light. The cosmic microwave background radiation we observe today comes from this moment, and imprinted in its tiny temperature variations, we can see the pattern of those primordial density fluctuations. Slightly hotter regions correspond to slightly denser regions. Slightly cooler regions correspond to slightly less dense regions. After recombination, gravity began sculpting these density variations into structure. Regions that were even slightly denser than average had a tiny bit more gravitational pull, which attracted surrounding matter, making them denser still. This is gravitational instability. a runaway process where overdense regions become more overdense and underdense regions become more underdense. But there's a subtlety here. In the early universe, ordinary matter, baryons, which are protons, neutrons, and electrons, was still coupled to radiation through frequent interactions. This coupling created pressure that resisted gravitational collapse on small scales, effectively preventing structure from growing in the ordinary matter. However, dark matter, which we now know makes up about 85% of all matter in the universe, doesn't interact with radiation. Dark matter could freely collapse under gravity, forming the gravitational wells into which ordinary matter would later fall. As the universe expanded and cooled, dark matter began forming an intricate network of filaments and halos. Computer simulations that track billions of dark matter particles through cosmic time show this process beautifully. Initially, the distribution is nearly smooth with only tiny variations. But as gravity works, the variations grow. Dark matter particles in overdense regions move toward each other, while particles in underdense regions drift apart or are pulled toward nearby overdensities. Over hundreds of millions of years, this process produces the cosmic web. Dark matter flows along paths determined by the gravitational potential landscape, channeling into one-dimensional filaments, two-dimensional sheets, and three-dimensional nodes, the densest regions where filaments intersect. The regions left behind, the underdense zones from which matter has evacuated, become the voids. The voids don't just appear suddenly. They grow and evolve. A region that starts 10% less dense than average will, through gravitational evolution, become progressively emptier as matter flows out towards surrounding overdensities. Meanwhile, cosmic expansion works to expand the void, stretching it to larger physical sizes. The interplay between gravitational evacuation and cosmic expansion determines the ultimate size and depth of voids. Ordinary matter eventually falls into the dark matter structure, following the gravitational potential wells that dark matter has carved. Gas flows into filaments, heats through compression, and eventually cools to form galaxies. This process is not perfectly efficient. Some gas remains in the filaments, never forming stars, and some stays in the voids as diffuse material at very low density. The formation timescale for voids depends on their size. Small voids, tens of millions of light-years across, could form relatively early in cosmic history, within the first few billion years after the Big Bang. Larger voids take longer to develop, as the gravitational evacuation process scales with the size of the region. The largest voids we observe today, hundreds of millions of light-years across, have been growing throughout the entire history of the universe and are still evolving. The shapes of voids, whether they're spherical or elongated, depend on the large-scale flows of matter around them. A void surrounded symmetrically by overdensities might evolve into a roughly spherical structure. A void embedded in a more complex environment, perhaps flanked by filaments on opposite sides, might stretch into an elongated shape. The velocity field of dark matter and gas flowing around and through the void determines its ultimate geometry. One fascinating aspect of void formation is that it's a continuous process. Voids don't reach some final state and then stop evolving. As the universe expands and ages, existing voids continue to grow and empty out. New voids can form from regions that are currently only mildly underdense. The void population today differs from the void population billions of years ago, and it will differ from the void population billions of years in the future. Modern simulations can follow void evolution with exquisite detail. By starting with initial conditions that match the observed cosmic microwave background and then evolving billions of particles forward in time using the equations of gravity and hydrodynamics, cosmologists can watch voids form, grow, merge, and interact with surrounding structures. These simulations reproduce the observed properties of real voids remarkably well, giving us confidence that we understand the basic physics of void formation. The few galaxies that do exist in voids typically formed in the rare regions where local overdensities persisted, despite the overall underdensity of the void environment. These isolated patches of higher density provided sufficient gravitational attraction to pull together enough gas to form a galaxy. But the low overall density of the Butsa void means these galaxies evolve differently than galaxies in denser environments, remaining more isolated and experiencing fewer of the interactions that shape galaxy evolution elsewhere. Void formation, then, is the flip side of structure formation. Every filament, every galaxy cluster represents matter that evacuated the voids. The cosmic web is a zero-sum arrangement. You can't build up overdensities without creating underdensities. The voids are the necessary consequence of gravitational structure formation, the empty spaces between where gravity has pulled matter together. Understanding how they form means understanding one of the fundamental processes shaping the universe. Humans have always had a tendency to think of our cosmic neighborhood as typical, representative of the universe as a whole. But as our understanding of large-scale structure has deepened, we've learned that our local environment is, in some ways, quite special. The Milky Way resides not in the depths of a void, but not in a dense cluster either. We inhabit an intermediate environment, on the outskirts of a modest cluster of galaxies called the local group, which itself lies near the edge of a substantial underdense region known as the local void. The local void was identified in the 1980s as part of the same galaxy surveys that revealed the cosmic web structure. Located in the direction of the constellation Sculptor, about 60 million light-years away from us, this void spans approximately 150 million light-years across. It's not the largest void in the nearby universe. That distinction belongs to the larger Boötes void, but it's notable for being so close to our cosmic home. The local void's proximity makes it an ideal laboratory for studying void properties in detail. Astronomers can detect even relatively faint galaxies within it, giving us a more complete picture of void galaxy populations than we can obtain for more distant voids. Studies have identified a few dozen galaxies within the local void, most of them small, low-mass systems with active star formation. These void galaxies appear bluer and more gas-rich than typical galaxies found in denser environments, consistent with the idea that they've evolved in relative isolation. But the local void's most interesting property might be its effect on our cosmic neighborhood's motion. Our local group of galaxies is not at rest in the reference frame defined by the cosmic microwave background radiation. Instead, we're moving at about 630 kilometers per second toward a region of sky in the direction of the constellation Centaurus. This motion is called our peculiar velocity, the component of our motion that's not due to the cosmic expansion. For decades, astronomers have worked to understand what's driving this peculiar velocity. Part of the motion is attributed to the gravitational attraction of overdense regions in that direction, particularly the Virgo cluster and the larger Shapley supercluster beyond it. These massive structures pull on our local group. But there's another component. The local void behind us is pushing, in a sense, by providing less gravitational attraction than the average cosmic density would provide. Think of it this way. Overdense regions pull harder than average, while underdense regions pull less than average. From the perspective of a galaxy or group of galaxies, this creates an effective repulsion from voids. The local group finds itself gravitationally attracted toward the Virgo Centaurus overdensities ahead of us and effectively repelled by the local void behind us. The net effect of both the pull and the push determines our peculiar velocity. Mapping the local void's boundaries and measuring the velocities of galaxies around it has allowed cosmologists to study how voids affect local dynamics. These studies reveal that the void's influence extends beyond its formal boundaries. Galaxies surrounding the void show systematic patterns in their motions, flowing away from the void center as they're pulled toward surrounding overdensities. This velocity field provides information about the void's mass deficit and its growth rate. The local void also affects how we interpret cosmological measurements. When we measure the expansion rate of the universe by observing distant galaxies, we're implicitly assuming that our local environment is representative of the average cosmic density. But if we sit near a void, our local expansion rate might differ slightly from the global average. This local void effect is small, but potentially relevant for precision cosmology, particularly for efforts to measure the Hubble constant, the current expansion rate of the universe. Some researchers have suggested that the local void might help explain an apparent tension in cosmology known as the Hubble tension. Different methods of measuring the universe's expansion rate give slightly different answers, with the discrepancy persisting despite careful efforts to understand systematic uncertainties. One proposal is that the local void creates a local expansion rate that differs from the global rate, potentially reconciling different measurements. This idea remains debated, with most cosmologists skeptical that the effect is large enough to fully explain the tension, but it illustrates how void environments can affect cosmological measurements. Beyond its scientific interest, the local void provides a contemplative perspective on our cosmic situation. We live at the edge of emptiness, with a vast underpopulated region extending away from us in one direction, while the richly populated Virgo cluster and its larger supercluster structure stretch in another direction. We're not in the heart of the cosmic web, but neither are we lost in the depths of a void. We occupy a sort of cosmic suburb, close enough to the city center to see its lights, yet with empty wilderness nearby. If you could observe the universe from within the local void rather than from our position at its edge, your view would be dramatically different. Nearby galaxies would be rare and faint. The rich clusters and groupings that dominate our local sky would be distant smudges. The universe would seem emptier, lonelier, more spread out. Cosmology conducted from deep within a void would face different challenges, as nearby galaxy samples would be smaller and observational horizons would need to extend further to sample representative cosmic structure. The local void reminds us that cosmic structure exists on scales that vastly exceed our intuitive understanding. We can map our local region, identify its underdensities and overdensities, and place ourselves within the larger cosmic web. But we can't step back and see it all at once. We're embedded in the structure we're trying to understand, like inhabitants of a vast foam trying to comprehend the bubble we're in and how it relates to all the other bubbles around us. As we'll see in later chapters, the local void is just one of countless voids filling the universe. Its proximity makes it special for detailed study, but the physics operating here operates in voids everywhere. By understanding our local underdensity, we learn about void physics throughout cosmic space and time. Among the vast collection of cosmic voids, some stand out for their extraordinary size, reaching scales that challenge our understanding of structure formation and test the limits of what cosmological models predict. These supergiant voids, hundreds of millions of light-years across, represent the most extreme underdensities in the observable universe. They raise questions about cosmic variance, the maximum possible void size, and whether their existence is consistent with standard cosmology. The Boötes void remains perhaps the most famous of these supergiant structures. Discovered in 1981 by Robert Kirshner and his colleagues during a galaxy redshift survey, it appeared as a stunning absence of galaxies in a region of sky toward the constellation Boötes. Initial observations suggested a spherical region approximately 330 million light-years in diameter, containing only about 60 galaxies. An astonishing underdensity given that a typical region of this size should contain 2,000 or more galaxies. The discovery generated significant excitement and some controversy in the astronomical community. Such a large, empty region seemed difficult to reconcile with the cosmological models of the time. Some researchers suggested exotic explanations, including the possibility that the void represented a different phase of space or the remnant of some unusual process in the early universe. Media reports dubbed it the Great Nothing, and sometimes exaggerated its emptiness, occasionally claiming it contained no galaxies at all. As observations continued and improved, the picture of the Boötes void became more nuanced. More careful surveys revealed additional galaxies within the void, bringing the total to perhaps 100 or more, though still far fewer than would exist in a normally dense region. The void turned out to be not perfectly spherical, but somewhat elongated, and not completely empty, but rather containing a typical void galaxy population of small, blue, gas-rich systems. Nevertheless, it remains one of the largest and emptiest known voids, a striking feature of the cosmic web within the relatively nearby universe. The Eridanus supervoid presents an even more intriguing case. This enormous underdensity, located in the direction of the constellation Eridanus, came to public attention not through galaxy surveys, but through its potential connection to an anomaly in the cosmic microwave background. Astronomers had noticed a surprisingly large cold spot in the microwave background map, a region where the temperature was about 70 microkelvins cooler than average, spanning several degrees across the sky. In 2007, researchers proposed that this cold spot might be explained by the integrated Sachs-Wolf effect associated with a supergiant void. When cosmic microwave background photons pass through a large void, they lose a tiny bit of energy due to the expansion of space within the void, arriving at Earth slightly cooler than they would if they'd traveled through normally dense regions. A sufficiently large void along the line of sight could potentially explain the observed cold spot. Subsequent surveys confirmed the existence of an enormous void in the direction of the cold spot, with estimates of its size ranging from 600 million to more than 1 billion light-years across, making it potentially the largest known structure in the observable universe. However, the connection between the void and the cold spot remains debated. Some analyses suggest the void isn't quite large or empty enough to fully explain the temperature anomaly, while others argue that the association could be coincidental. The Eridanus supervoid raises fundamental questions. If it is indeed as large as some estimates suggest, can standard cosmology explain how such a structure formed in the age of the universe? The growth of voids is limited by the time available since the Big Bang and by the properties of dark energy, which affects cosmic expansion. Voids can only grow so large in the time available. Finding voids at or beyond the predicted maximum size could indicate problems with our cosmological models or suggest modifications to our understanding of gravity, dark energy, or structure formation. Other supergiant voids have been identified in different regions of sky. The giant void in Canes Venatici, discovered in Sloan Digital Sky survey data, spans approximately 300 million light-years. The Capricornus void and several others of comparable size have been catalogued in various surveys. Each of these represents a substantial underdensity that formed through the gravitational evacuation process we discussed earlier, but on the largest possible scales. Studying supergiant voids helps cosmologists understand cosmic variance, the natural variation in structure that occurs just by chance in different regions of the universe. Even if the universe is statistically homogeneous on very large scales, any finite region will show variations from the average. Sometimes those variations are substantial. A region might happen to be overdense or underdense by more than you'd typically expect. Supergiant voids might represent the extreme tail of this statistical distribution, rare but not impossible fluctuations in cosmic structure. The abundance of supergiant voids, how many exist as a function of size, provides a sensitive test of cosmological models. Different models of dark energy, different values of cosmological parameters, and different theories of gravity all predict slightly different void abundance functions, particularly at the large size end. By counting how many supergiant voids exist in large volume surveys and comparing this to predictions, cosmologists can constrain these models. Some modified gravity theories, which propose alternatives to dark energy for explaining cosmic acceleration, predict more or larger voids than standard cosmology. This happens because modified gravity can change how quickly structure grows, potentially allowing voids to reach larger sizes in the available time. If we found significantly more or larger voids than standard cosmology predicts, it might favor these alternative theories. So far, observations appear broadly consistent with standard cosmology, but the statistics remain somewhat uncertain due to the small number of supergiant voids in surveyed regions. The psychological impact of supergiant voids shouldn't be underestimated. These structures are so vast that light takes hundreds of millions of years to cross them. If you could somehow travel through one, even at speeds approaching the speed of light, the journey would exceed the entire age of human civilization many times over. The scales involved are so far beyond human experience that they strain our ability to comprehend. Yet they exist, vast empty regions through which photons from the early universe pass on their way to our telescopes, affected only subtly by the gravitational potential gradients they encounter. Supergiant voids represent extremes of cosmic structure, the largest, emptiest regions we can identify. They're rare, requiring large survey volumes to find even a few examples. They're challenging to study in detail, as their enormous volumes make it difficult to obtain complete galaxy catalogues within them. Yet they're crucial for understanding the full range of cosmic structure, and for testing whether our cosmological models can explain not just the typical universe, but also its most extreme manifestations. When astronomers first discovered cosmic voids, the natural question was whether they contained any galaxies at all. Early observations suggested near total emptiness, with galaxy searches within void boundaries, turning up far fewer objects than equivalent regions elsewhere. But as surveys became more sensitive and complete, a more nuanced picture emerged. Voids aren't completely devoid of galaxies. Rather, they contain a sparse population of unusual galaxies, whose properties differ systematically from galaxies in denser environments. The galaxies that inhabit voids are predominantly small, low-mass systems. Massive elliptical galaxies and large spirals like the Milky Way are extraordinarily rare in void interiors. Instead, void galaxies tend to be dwarf irregulars, small spirals, and other low luminosity types. Their total stellar masses typically range from about 1 million to 1 billion solar masses, compared to the 100 billion solar masses or more characteristic of large galaxies in clusters and groups. One of the most striking characteristics of void galaxies is their color. In astronomy, galaxy color serves as a rough indicator of stellar age and current star formation rate. Blue galaxies contain hot, young stars formed recently, indicating ongoing star formation. Red galaxies contain predominantly older stars and have little active star formation. The galaxy populations in clusters and filaments show a mixture of colors, with many passive red galaxies alongside actively star-forming blue ones. Void galaxies, by contrast, are predominantly blue. Surveys consistently find that the fraction of blue galaxies increases as you move from high-density regions into filaments, and increases further into voids. In the emptiest void interiors, nearly all galaxies show active star formation, with blue colors indicating the presence of young, hot stars. This suggests that void galaxies have experienced less of the environmental processes that shut down star formation in denser regions. The gas content of void galaxies tells a similar story. Observations in the 21-centimeter radio line emitted by neutral hydrogen, the primary fuel for star formation, reveal that void galaxies are rich in gas relative to their stellar masses. While galaxies in clusters often have their gas stripped away by environmental effects, void galaxies retain their gas reservoirs, allowing star formation to continue over cosmic time. The evolutionary history of void galaxies appears to have been quieter than that of their cousins in denser environments. In clusters and along filaments, galaxies frequently interact with each other, sometimes merging, sometimes passing close enough for gravitational tides to distort their structures and trigger bursts of star formation. These interactions and mergers are major drivers of galaxy evolution, affecting everything from morphology to star formation rate to central black hole growth. Void galaxies, by contrast, evolve in isolation. The vast distances between galaxies in voids mean that close encounters are rare. A void galaxy might go billions of years without experiencing any significant interaction with another galaxy. This isolation allows void galaxies to evolve more quiescently, steadily forming stars from their gas reservoirs without the dramatic bursts and transformations common in denser environments. Interestingly, the few large galaxies that do exist in voids often show signs of recent or ongoing interaction, suggesting they formed through the merger of several smaller systems. These void supergiants are rare, but when found, they often display disturbed morphologies, tidal tails, or other evidence of past mergers. Their existence demonstrates that gravitational interactions can occur even in voids, though at much lower frequency than elsewhere. The chemical composition of void galaxies also reflects their evolution. Elements heavier than hydrogen and helium, what astronomers call metals, are produced in stars and distributed through space by supernovae and stellar winds. Over cosmic time, as generations of stars form, die, and enrich the interstellar medium, the metallicity of galaxies gradually increases. Void galaxies show slightly lower metallicities on average than galaxies of similar mass in denser environments, consistent with their slower, more isolated evolution. Studying void galaxy populations helps astronomers understand galaxy evolution more generally by providing examples of systems that evolved without strong environmental influences. In this sense, void galaxies serve as control samples, showing what happens when gravitational interactions and environmental processes are minimal. Differences between void galaxies and their counterparts elsewhere can be attributed to environmental effects rather than internal galaxy properties. The distribution of void galaxies within voids is not uniform. Rather than being scattered randomly throughout void volumes, galaxies tend to cluster in small groups or to line up along tenuous filaments within the voids. This substructure within voids reflects the hierarchical nature of cosmic structure formation. Even within an underdense region, there are local overdensities where galaxies can form and persist. Some void galaxies are found quite close to void boundaries, where the transition from underdense to average density regions occurs. These edge galaxies share properties intermediate between typical void galaxies and typical filament galaxies, showing that the environmental effects of density vary continuously rather than switching abruptly at some boundary. The discovery and characterization of void galaxy populations required dedicated observational campaigns. Because these galaxies are faint and sparse, finding them demands deep, wide-area surveys that can detect low luminosity systems over large volumes. The Sloan Digital Sky Survey and subsequent surveys provided the necessary data, allowing researchers to identify void galaxies systematically and study their properties statistically. For void dwellers, if any intelligent civilizations inhabit void galaxies, the universe would appear profoundly lonely. The nearest large galaxy might be tens of millions of light years away, visible only as a faint smudge, even through powerful telescopes. The rich clusters and supercluster structures that dominate our sky would be distant or absent altogether. Cosmology from a void galaxy would require observing extremely faint and distant objects to build up a picture of cosmic structure. Yet void galaxies are not isolated from the universe. They're connected to the cosmic web through the same gravitational forces that shape all structure. They're bathed in the cosmic microwave background radiation. They're reached by light from distant galaxies and quasars. They participate in the cosmic expansion. They're part of the same universe as everything else, just in a less populated neighborhood. Understanding void galaxies helps complete our picture of galaxy evolution across all environments, from the densest clusters to the emptiest voids, encompassing the full range of conditions under which galaxies form and evolve in our universe. While the scarcity of visible galaxies defines cosmic voids in observational terms, the dark matter distribution tells a somewhat different story. Dark matter, the invisible substance that makes up about 85% of all matter in the universe, exists in voids just as it does everywhere else, but at significantly lower density than the cosmic average. Understanding dark matter in voids is crucial for comprehending void physics and the overall structure of the cosmic web. Dark matter doesn't emit, absorb, or scatter light, making it invisible to telescopes. We know it exists through its gravitational effects. It holds galaxies and galaxy clusters together, affects the motion of galaxies within clusters, and gravitationally lenses light from distant sources. Dark matter also provides the gravitational scaffolding onto which ordinary matter falls during structure formation. Without dark matter, the cosmic web, as we observe it, could not have formed in the time available since the Big Bang. In voids, dark matter exists at roughly 10 to 20% of the average cosmic density, significantly underdense but not absent. This dark matter is distributed in a hierarchical structure of halos and subhalos, much like everywhere else, but with lower number density and smaller typical masses. While the densest regions of the universe contain dark matter halos, with masses exceeding 1,000,000 billion solar masses, hosting massive galaxy clusters, void regions contain primarily small halos with masses ranging from perhaps 1 billion to a few 100 billion solar masses. Many of these dark matter halos in voids are dark in every sense. They contain no visible galaxies at all. Cosmological simulations predict vast numbers of low-mass dark matter halos throughout space, including within voids. Only the more massive halos collect enough gas to cool and form stars, creating visible galaxies. Halos below a certain mass threshold remain dark, containing gas, but no stars. Voids are populated by many such invisible halos. The distribution of dark matter in voids affects the gravitational potential throughout these regions. Even though voids are underdense overall, local variations in dark matter density create gravitational potential wells and hills. These potential variations are small compared to those in denser regions, but they're still significant enough to affect the motion of any galaxies present and to influence how gas and dark matter flow through the void. Detecting dark matter in voids directly is extremely challenging. The most promising method is gravitational lensing, the bending of light by mass. When light from a distant galaxy passes through a foreground region containing mass, the light path bends, potentially creating multiple images, distorting shapes, or magnifying brightness. Strong lensing effects, which create dramatic multiple images, require high mass concentrations found in galaxy clusters, not in voids. However, weak gravitational lensing, subtle statistical distortions in the shapes of many background galaxies can potentially detect matter in voids. By measuring the shapes of millions of distant galaxies and looking for correlated distortions, astronomers can map the foreground matter distribution, including underdense regions. This technique has been used to confirm that voids are indeed matter-deficient regions and to measure the degree of underdensity. Another indirect probe of void dark matter comes from studying the motion of galaxies near void boundaries. Galaxies respond gravitationally to the local matter distribution, and their velocities encode information about the gravitational potential, which depends on both the visible and dark matter. By measuring galaxy velocities around and within voids, astronomers can infer properties of the dark matter distribution. The small dark matter halos within voids might host low-mass dwarf galaxies too faint to detect with current technology. Future extremely deep surveys might reveal populations of ultra-faint dwarf galaxies in voids, which would indirectly trace the dark matter halo distribution. The number of visible galaxies as a function of dark matter halo mass, the so-called galaxy halo connection, remains an active area of research, particularly for low-mass halos in underdense environments. Dark matter in voids also provides a test case for alternative dark matter theories. While the standard model assumes dark matter consists of cold, collisionless particles that interact only gravitationally, alternative proposals suggest different possibilities: warm dark matter, self-interacting dark matter, or modifications to gravity that eliminate the need for dark matter altogether. These alternatives make different predictions for structure on small scales, particularly in underdense regions. The abundance and properties of small halos in voids could potentially distinguish between competing theories. For example, warm dark matter, where dark matter particles have higher velocities than in the cold dark matter scenario, would suppress the formation of small dark matter halos. This would reduce the number of small halos in voids compared to cold dark matter predictions. Precision measurements of void structure could thus constrain dark matter properties. Self-interacting dark matter, which includes scenarios where dark matter particles scatter off each other, might produce dark matter halos with different internal structures than standard cold dark matter. While these effects are most easily studied in high-density halos in clusters, the halos in voids, evolving in isolation, might show distinctive signatures if dark matter self-interacts. Modified gravity theories, which propose to explain galactic rotation curves and other dark matter evidence through modifications to general relativity rather than through invisible matter, make predictions about structure formation that differ from dark matter models. Void properties, their sizes, depths, and evolution depend on the theory of gravity and could potentially discriminate between general relativity plus dark matter and modified gravity theories. The evolution of dark matter distribution in voids over cosmic time follows the same gravitational dynamics that govern structure formation everywhere. Early in cosmic history, voids were less empty, containing higher dark matter densities. As structure evolved, dark matter flowed from underdense regions toward overdense ones, emptying the voids while building up filaments and clusters. This evacuation process continues, though at an ever-decreasing rate as the matter distribution approaches its equilibrium configuration. Looking toward the deep future of the universe, dark matter in voids will continue to thin out as cosmic expansion proceeds. In the distant epochs ahead, trillions of years from now, when the universe has expanded many times its current size, the dark matter density in voids will have decreased to levels almost indistinguishable from empty space. The halos will grow ever more isolated, their random motions carrying them on trajectories that will never bring them close to other halos. Dark matter in voids thus represents a crucial but largely invisible component of void physics. It provides the gravitational framework within which the visible components, gas and galaxies, evolve. Understanding its distribution and properties helps us understand void formation, void evolution, and the nature of dark matter itself. The voids, despite their emptiness, remain bound by the same dark matter that structures all of space. Between the few galaxies scattered through cosmic voids lies another component that's easy to overlook: diffuse intergalactic gas, spread thinly across vast distances, heated to temperatures reaching millions of degrees, and carrying information about cosmic history and void physics. This warm, hot, intergalactic medium represents the majority of the ordinary matter in voids, vastly outmassing the stars in the sparse void galaxy population. When we account for all the ordinary matter, baryons, in physics terminology, in the universe, we find an interesting discrepancy. The cosmic microwave background radiation and Big Bang nucleosynthesis calculations tell us how much ordinary matter exists total, about 4 to 5% of the universe's total energy budget. But when we count up all the baryons we can see in stars, galaxies, and cold gas, we account for less than half of this total. Where's the missing ordinary matter? Much of it resides in this warm, hot intergalactic medium, heated to temperatures between 100,000 and 10 million Kelvin, existing at densities far too low to form stars or even to emit much radiation. This material is extraordinarily difficult to detect directly. It's too hot to emit the 21-centimeter hydrogen line used to detect cold gas. It's often too cool to emit much X-ray radiation, the primary signature of the hottest intergalactic gas in galaxy clusters. It occupies an observational blind spot between the techniques used for cold gas and hot plasma. In voids, this intergalactic medium exists at even lower densities than in filaments or sheets, perhaps only 10 to 100 hydrogen atoms per cubic meter, compared to tens of thousands per cubic meter in filaments. For reference, Earth's atmosphere at sea level contains about 10 to the power of 25 molecules per cubic meter. Even the dense filament gas is a vacuum beyond anything achievable in laboratory settings, and void gas is 10 to 100 times thinner still. Despite these incredibly low densities, the gas in voids can reach high temperatures through several processes. As cosmic structure forms and matter flows from voids into filaments, the kinetic energy of that flow converts to heat through shock waves and gravitational compression. Gas falling into the gravitational potential wells of dark matter halos releases energy, heating itself and surrounding material. And in some regions, energetic processes associated with galaxies and quasars, outflows, jets, supernova-driven winds, can inject energy into the intergalactic medium, raising its temperature. The ionization state of void gas provides information about the radiation environment. Nearly all of the gas is ionized, electrons stripped away from hydrogen atoms, because of the extragalactic background radiation. This radiation, produced by all the stars, galaxies, and quasars throughout cosmic history, maintains a background radiation field that keeps intergalactic hydrogen ionized. The ionization fraction depends on the balance between ionizing radiation and recombination of electrons with protons, with the result that even in voids, the gas is more than 99% ionized. Detecting void gas directly requires clever observational techniques. One approach uses absorption line spectroscopy. When light from a distant bright quasar passes through intervening gas on its way to Earth, that gas absorbs specific wavelengths corresponding to electronic transitions in the atoms present. By studying these absorption lines in quasar spectra, astronomers can map the intergalactic medium along the line of sight, including gas in underdense regions. This technique, called the Lyman alpha forest, reveals that the intergalactic medium is not smoothly distributed, but shows structure reflecting the underlying cosmic web. Denser regions produce stronger absorption features, while underdense void regions produce weaker absorption or gaps in the forest. By analyzing many quasar sightlines, researchers can statistically characterize void gas properties. Another detection method exploits the fact that the warm-hot intergalactic medium, when present at its highest densities and temperatures, can produce detectable X-ray emission or absorption. Space-based X-ray telescopes have searched for these signatures along specific sightlines and in stacking analyses that combine signals from many directions. These observations suggest the presence of the predicted warm-hot medium, though uncertainties remain about its exact density, temperature distribution, and contribution to the overall baryon budget. The chemical composition of void gas reflects cosmic chemical enrichment history. When massive stars explode as supernovae, they disperse heavy elements produced through nuclear fusion into surrounding space. Over time, these elements mix into the intergalactic medium, enriching it beyond the primordial composition of hydrogen and helium. Even void gas shows some level of metal enrichment, indicating that material processed through stars has reached even these remote regions. The distribution of metals in void gas is likely quite inhomogeneous. Near the few galaxies present in voids, metallicity might be relatively high, where galactic winds have pushed enriched material into intergalactic space. Far from any galaxies, in the true intergalaxy voids, metallicity might be much lower, closer to primordial values. Mapping this metallicity distribution would provide insight into how enriched material propagates through the cosmic web. Void gas plays a role in cosmic energy transport. When energetic events like supernova explosions or active galactic nuclei inject energy into the intergalactic medium, that energy can propagate through the gas via sound waves, shocks, or other mechanisms. Even in voids, these energy injection events can affect gas over large distances, heating it, ionizing it more completely, or driving outflows. The pressure of void gas, though minuscule compared to everyday experience, is not zero. This pressure, combined with the gravitational potential, determines the gas distribution and any motions. In the deepest underdensities within voids, gas pressure pushes outward, while gravity, or lack thereof, provides little restoring force, allowing gas to flow outward toward void edges or to remain in place, depending on the detailed potential structure. Looking toward the future evolution of void gas, several factors come into play. Continued cosmic expansion dilutes the gas density further, making it even more tenuous. Ongoing star formation and galaxy evolution inject additional energy and metals, though at low rates given the sparse galaxy populations. And the gradual cooling of the universe as it expands affects gas temperature, potentially allowing some material to cool and become neutral over extremely long timescales. The intergalactic gas in voids represents one of the last frontiers in accounting for cosmic baryons. While we've made progress in detecting and characterizing this material, significant uncertainties remain. Future instruments, particularly X-ray telescopes with greater sensitivity and spectral resolution, should improve our ability to directly detect and map the warm-hot intergalactic medium in voids and elsewhere. Understanding void gas completes the picture of what actually inhabits these supposedly empty regions. Between the dark matter halos, alongside the sparse galaxy population, filling the vast spaces between, lies this diffuse medium, carrying the majority of the ordinary matter in voids, invisible, tenuous, but fundamentally part of the cosmic structure. Cosmic voids, despite their sparse matter content, are not dark in the way we might imagine. They're filled with radiation crossing from every direction, ancient photons from the Big Bang, high-energy particles traveling at nearly the speed of light, electromagnetic radiation from distant galaxies and quasars, and even gravitational waves rippling through space-time itself. These radiation fields provide probes of void properties and connect voids to the rest of the universe. The most famous radiation field permeating all of space, including voids, is the cosmic microwave background. These photons were emitted about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen, making space transparent for the first time. Since then, these photons have been traveling through space, their wavelengths stretched by cosmic expansion from visible light into microwaves. The cosmic microwave background provides a nearly perfect blackbody radiation field with a current temperature of about 2.7 Kelvin. This radiation fills voids just as it fills every other region of space. However, when cosmic microwave background photons pass through voids, something subtle happens. They experience a tiny energy change due to the gravitational potential gradient of the void. This phenomenon, called the integrated Sachs-Wolf effect, occurs when photons traverse a region where the gravitational potential is changing over time. As cosmic expansion proceeds and voids evolve, their gravitational potentials become less negative. The underdensity grows deeper, gravitationally speaking. Photons entering a void experience a gravitational blue shift as they fall into the potential well, gaining energy. When they exit, they experience a red shift as they climb back out. In a static universe, these effects would exactly cancel. But in an expanding universe, particularly one accelerating due to dark energy, the void's potential changes while the photon is crossing. The photon exits a void that's gravitationally deeper than the one it entered, resulting in a net energy loss. The photon arrives at our telescopes slightly cooler than it would if it had traveled through a region of average density. By statistically analyzing cosmic microwave background maps for correlations with known void locations, astronomers can detect this effect and use it to study dark energy and void evolution. Beyond the cosmic microwave background, voids are traversed by optical and infrared radiation from distant galaxies. The extragalactic background light, the combined glow of all galaxies throughout cosmic history, propagates through voids just as through denser regions. This radiation helps maintain the ionization of intergalactic gas and provides a background against which closer objects appear. High-energy photons, including ultraviolet radiation, X-rays, and gamma rays, also cross voids. These photons are produced by energetic processes: hot gas in galaxy clusters, active galactic nuclei powered by supermassive black holes, supernovae, and other violent events. The extragalactic gamma-ray background, detected by space telescopes, includes contributions from sources throughout cosmic space, with photons having crossed voids and filaments alike on their journeys to Earth. Voids are also traversed by cosmic rays, high-energy particles, primarily protons and atomic nuclei, accelerated to enormous energies by astrophysical processes. The highest energy cosmic rays, with energies exceeding a quintillion electron volts, travel nearly undeflected by galactic and intergalactic magnetic fields, moving in approximately straight lines through space. Some of these particles cross cosmic voids, and their interactions with the cosmic microwave background radiation produce cascades of particles that can be detected. One particularly interesting component is neutrinos. These weakly interacting particles are produced in vast numbers by stars, supernovae, and the Big Bang itself. The cosmic neutrino background, analogous to the cosmic microwave background, but consisting of neutrinos rather than photons, fills all space, including voids. Neutrinos interact so weakly with matter that they pass through planets, stars, and even galaxies almost without effect. Voids, being relatively empty, present even less obstacle to these ghostly particles. The density of the cosmic neutrino background in voids differs only slightly from that in denser regions, as neutrino trajectories are barely affected by gravitational potentials they encounter. However, the large-scale neutrino distribution does trace cosmic structure to some degree, with neutrinos moving preferentially along certain trajectories determined by the gravitational potential landscape. This creates subtle clustering of neutrinos that might, in principle, be detectable through their tiny gravitational effects. Gravitational waves also propagate through voids. These ripples in spacetime, produced by accelerating masses and most dramatically by merging black holes or neutron stars, travel at the speed of light and are affected very little by intervening matter. A gravitational wave crossing through a void versus through a filament experiences essentially the same propagation, as the gravitational wave doesn't interact with matter or radiation electromagnetically. However, gravitational waves can be affected by gravitational lensing, their paths bent by massive structures they pass near. A gravitational wave signal that happens to pass through or near a massive galaxy cluster will experience lensing effects that slightly modify its observed properties. A wave that crosses a void rather than passing near massive structures might arrive at Earth with slightly different characteristics, though this effect is generally small. The radiation fields in voids serve as probes of cosmology. By studying how different types of radiation propagate through voids, whether photons, neutrinos, cosmic rays, or gravitational waves, astronomers can test fundamental physics and cosmological models. The integrated Sachs-Wolf effect in the cosmic microwave background constrains dark energy properties. Gamma-ray propagation tests our understanding of extragalactic magnetic fields and the diffuse radiation background. Gravitational wave propagation tests general relativity on cosmic scales. For a hypothetical observer in a void galaxy, these radiation fields would be the main connection to the wider universe. Visible light from distant galaxies would be faint but present. The cosmic microwave background would be detectable with appropriate instruments, showing the same large-scale pattern of hot and cold spots visible from Earth, providing evidence of cosmic structure and the Big Bang origin. High-energy particles and photons would occasionally arrive, carrying information about distant energetic events. The fact that radiation crosses voids so freely, unimpeded by the sparse matter, makes voids excellent laboratories for studying that radiation. Propagation effects that might be complicated by interactions with matter in denser regions are simpler in voids. Observations through or from within voids might offer particularly clean views of distant objects or clear measurements of background radiation fields. Radiation fields remind us that voids, while matter-poor, are not disconnected from the universe. They're embedded in the same cosmos as everything else, crossed by the same radiation, bathed in the afterglow of the Big Bang, connected by light and particles to distant structures. The voids are part of the whole, even if they represent the negative space within that whole. Among the most mysterious and poorly understood aspects of cosmic voids is the presence of magnetic fields. Despite the extreme thinness of matter in these regions, observations and theoretical models suggest that magnetic fields permeate even the emptiest voids, threading through the intergalactic medium at incredibly low strengths, but potentially playing roles in cosmic evolution that we're only beginning to appreciate. Magnetic fields are ubiquitous in astrophysics. Earth has a magnetic field generated by dynamo processes in its liquid metal core. The Sun has complex magnetic fields that power solar flares and structure its corona. Galaxies harbor magnetic fields associated with their disks and halos. Galaxy clusters contain magnetic fields with strengths of several microgauss, millionths of the magnetic field strength at Earth's surface. But what about the spaces between? the filaments of the cosmic web and the voids. Do magnetic fields exist there too? And if so, where did they come from and how strong are they? Detecting magnetic fields in low-density intergalactic space is extraordinarily challenging. Magnetic fields don't emit light directly. They must be inferred through their effects on other phenomena. Several techniques have been developed to search for intergalactic magnetic fields, each with its own sensitivities and uncertainties. One method exploits the fact that high-energy gamma-ray photons traveling through space can interact with the extragalactic background light, producing electron-positron pairs. These charged particles then interact with the cosmic microwave background, producing lower-energy gamma rays. If magnetic fields are present along the path, the charged particles spiral around the field lines, and the cascade of secondary gamma rays arrives at Earth from slightly different directions than the original photon. By looking for these characteristic patterns in gamma-ray observations, astronomers can place limits on intergalactic magnetic fields. These studies suggest that magnetic fields with strengths greater than about 10 to the power of -16. Gauss exist in the intergalactic medium, even in relatively empty regions. For comparison, a refrigerator magnet produces a field of about 50 Gauss, and Earth's magnetic field is about 0.5 Gauss at the surface. So these intergalactic fields are extraordinarily weak by everyday standards. Yet they're not zero. Another technique studies the polarization of light from distant quasars and radio galaxies. As electromagnetic radiation propagates through a magnetized plasma, its plane of polarization rotates, an effect called Faraday rotation. The amount of rotation depends on the magnetic field strength and the electron density along the line of sight. By measuring Faraday rotation for many sources in different directions, astronomers can statistically infer properties of the intervening magnetic fields. These rotation measure studies have revealed magnetic fields in galaxy clusters and along filaments, with suggestions of weaker fields in void regions. However, extracting void magnetic field information specifically is difficult because the signal integrates contributions from all magnetized plasma along the line of sight, and the void contribution is necessarily small given the low density there. Where could these magnetic fields have come from? Several possibilities exist. One is that magnetic fields were present in the very early universe, perhaps generated during cosmic inflation or shortly thereafter. These primordial magnetic fields would have been stretched by cosmic expansion and would now exist throughout space, including in voids, at extremely low strengths. Voids might actually preserve primordial fields better than denser regions, as the magnetic field evolution in voids has been less affected by astrophysical processes. Alternatively, magnetic fields might have astrophysical origins, produced by galaxies and then transported into intergalactic space. Galactic winds, outflows of gas driven by supernova explosions and stellar winds, can carry magnetic fields from galaxies into surrounding space. Over cosmic time, this process might have magnetized much of the intergalactic medium, including regions far from galaxies. A challenge for the astrophysical origin scenario is explaining how magnetic fields reach the most remote void regions, far from any galaxies. The outflows from the sparse void galaxy population might not provide sufficient field strength or coverage. However, at earlier cosmic epochs, before voids were as empty as they are today, there may have been more galaxies present whose outflows could have magnetized the region before matter evacuated. The strength of magnetic fields in voids likely depends on distance from void boundaries and from the sparse galaxies within voids. Near void boundaries, where filaments of the cosmic web begin and galaxy density increases, magnetic fields are probably stronger, perhaps approaching 10 to the power of -11 or 10 to the power of -10 Gauss. In the deepest void interiors, Far from any galaxies, fields might be as weak as 10 to the power of -18 Gauss, or even weaker, so tenuous that they barely qualify as magnetic fields at all. These weak magnetic fields in voids might seem negligible, but they can have subtle effects. Magnetic fields affect the propagation of charged particles, causing them to spiral around field lines rather than traveling in perfectly straight trajectories. Even very weak fields can deflect lower energy cosmic rays, affecting their distribution. Magnetic fields also affect the diffusion and mixing of gas, potentially influencing how material flows through voids and into surrounding filaments. From a theoretical perspective, the topology of magnetic fields in voids is fascinating. Magnetic field lines must form closed loops or extend to infinity. They can't simply end. In a void, where matter density is so low, the magnetic field topology might be quite simple, with large-scale loops or fields that thread through the void from one boundary to another. Alternatively, the field might have a complex, tangled structure inherited from turbulent processes in the early universe or from the cumulative effect of many galactic outflows. Future observations will improve our understanding of void magnetic fields. Upcoming radio telescopes with improved sensitivity, such as the Square Kilometre Array, will detect polarized emission and Faraday rotation from many more sources, providing better statistical constraints. Gamma-ray observations will continue to probe magnetic fields through the cascade process described earlier, and theoretical simulations that include magnetohydrodynamics will predict magnetic field properties in voids with increasing accuracy. The presence of magnetic fields in voids, however weak, connects these regions to the broader electromagnetic environment of the universe. Voids are not isolated magnetic islands, but are part of the cosmic magnetic web, however tenuous the threads might be. Understanding these fields helps complete our picture of void contents and evolution. In the deep future of the universe, as cosmic expansion continues and voids grow emptier, these magnetic fields will evolve too. If the fields are frozen into the plasma, they'll be diluted by the expansion, becoming ever weaker. Eventually, in a universe trillions of years older than today, void magnetic fields might be so weak as to be effectively zero. A final trace of earlier epochs fading into the vacuum of deep cosmic time. The question of life in cosmic voids might seem absurd at first. These vast galaxy-poor regions appear so hostile to life, so devoid of the stars and planetary systems we associate with habitability, that asking whether life might exist there seems like asking whether fish could live in the Sahara Desert. Yet the question is worth contemplating, both as a thought experiment about the conditions necessary for life and as a genuine exploration of exotic cosmic environments where life might possibly arise. The fundamental requirement for life as we know it is stars. Stars provide energy through nuclear fusion, create heavy elements necessary for planets and chemistry, and illuminate planetary surfaces or drive planetary systems. Without stars, there's no energy source to power complex chemistry, no heavy elements to build complex molecules, no warmth to maintain liquid water or other solvents in which biochemistry might occur. Voids do contain stars. They're just extraordinarily rare compared to the rest of the universe. The sparse galaxy population in voids includes billions of stars total, probably hundreds of billions or even trillions when you account for all the small dwarf galaxies scattered through void volumes. These stars have planets, at least statistically. Planetary systems appear to be common outcomes of star formation regardless of galactic environment. So yes, technically, life could exist in the voids simply because voids contain stars and planets. A planet orbiting a star in a void galaxy would be physically indistinguishable from a planet orbiting a comparable star in the Milky Way. The local environment, the star's properties, the planet's composition, the presence of liquid water, would be the same. From a planetary perspective, it wouldn't matter that the nearest large galaxy was 50 million light-years away rather than 2 million. But would intelligent life arising in a void galaxy perceive the universe differently? The answer is certainly yes, and in profound ways. An astronomer on a planet in a void galaxy would see a fundamentally emptier cosmos. The nearest bright galaxies would be distant smudges requiring telescopes to resolve. There would be no Andromeda galaxy dominating the night sky, no nearby cluster like Virgo showing thousands of galaxies in a single region of sky. For such a civilization, discovering the cosmic web, learning that the universe is not as empty everywhere as it is in their neighborhood, would be a revelation requiring extremely deep observations. The same cosmological truths would eventually become clear. The expanding universe, the Big Bang origin, the cosmic microwave background, the large-scale structure. But the path to those discoveries would be more difficult, requiring more powerful instruments and more careful analysis. The nearest galaxy that might host other intelligent life would be vastly more distant than for civilizations in denser environments. If we use distance to the nearest large galaxy as a rough proxy for how isolated a civilization is, void civilizations would be among the most isolated in the universe. While we can see Andromeda with our naked eyes and could, in principle, imagine sending signals there, though they'd take 2.5 million years to arrive, a void civilization might need to contemplate signaling across 50 million light-years to reach the nearest galactic community. This isolation could have philosophical and psychological impacts on such a civilization. Would the emptiness of their cosmic neighborhood lead to feelings of loneliness or existential insignificance? Or would it foster a different perspective, perhaps seeing their rare galaxy as special precisely because of its isolation? Would void civilizations develop differently than those in richer environments, with their cosmologies and philosophies shaped by the emptiness around them? One intriguing possibility is that void galaxies, because of their isolation and the lower frequency of galaxy interactions, might be particularly stable environments for life. Galaxies that undergo mergers, common in clusters and along filaments, experience periods of increased star formation, supernova, rates, and potential disruption to planetary systems. A galaxy in a void might evolve more quiescently, providing a more stable environment over billions of years. However, this stability might come to cost. Galaxy interactions, while potentially disruptive, also trigger star formation and bring fresh gas into galactic disks, potentially creating more sites for planet formation and life. A void galaxy, evolving in isolation, might experience less intense star formation and fewer total planets over cosmic time. The trade-off between stability and opportunities for life is unclear. If void civilizations exist and develop spacefaring technology, their exploration of the cosmos would face unique challenges. Traveling to the nearest other galaxy would require journeys of tens of millions of light-years, feasible only for civilizations with extremely advanced technology, perhaps capable of generation ships lasting millions of years, or of some form of faster-than-light travel that physics currently says is impossible. Void civilizations would be among the most isolated in the universe, separated from other galactic communities by distances that dwarf the already enormous intergalactic separations typical elsewhere. Could life exist not in void galaxies, but somehow in the voids themselves, in the intergalactic medium? This seems extraordinarily unlikely given the absence of energy sources and the extreme thinness of matter. The intergalactic gas in voids exists at densities billions of times lower than interstellar gas within galaxies. There's no plausible energy source to power metabolism or complex chemistry. The radiation environment, while including cosmic rays and background radiation, doesn't provide the concentrated, usable energy that stars supply. Science fiction has occasionally explored scenarios of life in intergalactic space, perhaps beings that evolved to harness the energy of cosmic rays, or that exist as vast, diffuse structures spanning light years. While imaginative, these scenarios lack any observational evidence or even plausible theoretical mechanisms. They remain firmly in the realm of speculation rather than serious scientific possibility. The question of life in voids ultimately returns us to the question of life anywhere. We still don't know how common or rare life is in the universe as a whole. Until we discover life beyond Earth, whether in our solar system, elsewhere in the Milky Way, or in distant galaxies, we can't confidently assess the probability of life in any specific environment, including voids. If life is common, arising readily wherever conditions permit, then void galaxies surely host life, even if those living beings find themselves in one of the loneliest neighborhoods in the cosmos. If life is rare, requiring unusual conditions or improbable events, then perhaps void galaxies, lacking the complex environmental interactions of denser regions, are less likely to develop life, and void civilizations might be even rarer than civilizations elsewhere. What we can say is that void galaxies, while few and isolated, contain billions of stars and presumably billions of planets. The fundamental requirements for life, energy, complex chemistry, liquid solvents, stability over time, can exist there. Whether life has actually arisen in void galaxies remains unknown, but it's not impossible. And if it has, those life forms would experience a cosmos very different from our own, looking out at a universe that seems emptier, lonelier, and more mysterious than the relatively rich cosmic environment we inhabit. Among the most profound discoveries in cosmology over the past few decades is that the universe's expansion is accelerating. Something, given the placeholder name dark energy, is pushing space apart, causing galaxies to recede from each other at ever-increasing speeds. This acceleration affects how cosmic structure evolves, and cosmic voids provide one of the most sensitive tests of dark energy's properties and perhaps clues to its fundamental nature. The discovery of cosmic acceleration came primarily from observations of distant supernovae in the late 1990s. By measuring how bright these standard candle explosions appeared at different distances, astronomers could trace the expansion history of the universe. The surprising result was that the expansion, rather than slowing down due to gravitational attraction as expected, was speeding up. This discovery earned the 2011 Nobel Prize in Physics and reshaped our understanding of cosmology. Dark energy is characterized by its equation of state, the relationship between its pressure and energy density. For the simplest model, called the cosmological constant, this equation of state parameter equals -1, representing a constant energy density that doesn't change as the universe expands. Alternative models propose different values or even variations in the equation of state over time, potentially revealing clues about dark energy's fundamental nature. Cosmic voids are particularly sensitive to dark energy because they're regions where gravitational attraction is weak, and the effects of cosmic acceleration become relatively more important. In a universe without dark energy, voids would evolve differently than in a universe with dark energy. They'd grow more slowly, maintain different density contrasts, and show different shapes and abundance as functions of cosmic time. The basic physics is this: voids are under-dense regions from which matter has gravitationally evacuated, flowing towards surrounding overdensities. This process is resisted by cosmic expansion, which carries everything apart. In a universe with dark energy causing accelerated expansion, the expansion rate is higher than it would be otherwise, and this affects how quickly voids can grow and how deep they can become. Measuring void properties as functions of cosmic time, by studying voids at different redshifts, which corresponds to looking back to different epochs of cosmic history, reveals the evolution of void population. The abundance of voids as a function of their size, their average density contrasts, and how these properties change over billions of years all depend on cosmological parameters, including dark energy. Several specific tests use voids to constrain dark energy. One involves counting voids as a function of size at different cosmic epochs. Different dark energy models predict slightly different void abundance functions. By carefully measuring how many voids of each size exist at various redshifts and comparing to theoretical predictions, cosmologists can constrain the dark energy equation of state. Another test uses the Alcock-Paksinski effect, which compares the apparent shapes of voids. Because cosmic expansion differs in the radial direction, along the line of sight, and tangential directions, perpendicular to the line of sight, voids that are actually spherical will appear distorted unless we correctly account for the expansion history. By measuring void shapes and testing whether they're consistent with spherical symmetry, we can constrain cosmological parameters, including dark energy. The integrated Sachs-Wolf effect we discussed earlier provides another dark energy test. The amplitude of the cosmic microwave background temperature correlations with voids depends on dark energy properties, as dark energy affects how gravitational potentials evolve over time. Measuring this effect for known voids constrains dark energy models. Void-galaxy cross-correlations, studying how galaxy velocities and positions correlate with void locations, encode information about the growth rate of structure, which in turn depends on gravity and dark energy. Galaxies near void boundaries show systematic patterns in their velocities as they fall toward overdense filaments and away from underdense voids. The strength and pattern of these velocity flows test our understanding of gravity and cosmic acceleration. Why are voids particularly good for these tests compared to other cosmic structures? Several reasons. First, voids are simpler systems than clusters or galaxies. They contain fewer complications from baryonic physics, star formation, feedback, gas cooling, that can confuse theoretical predictions. Second, voids are large-scale structures where the effects of dark energy are relatively more important compared to the gravitational effects of matter. Third, voids are common enough that statistical studies are possible, but large enough that individual voids can be measured precisely. An alternative to dark energy that voids can help test is modified gravity. Instead of adding a dark energy component to general relativity, some theories propose that gravity itself behaves differently on cosmological scales than general relativity predicts. These modifications are designed to produce cosmic acceleration without requiring dark energy. Different, modified gravity theories make different predictions for structure formation, particularly for void properties. For example, certain modified gravity theories predict enhanced void growth rates compared to general relativity, plus dark energy. This happens because the modified gravitational force can differ in underdense regions compared to overdense ones, affecting how quickly voids empty out. By measuring void growth rates and comparing to predictions, we can test whether general relativity holds on cosmic scales or whether modifications are required. Current constraints from void studies are consistent with the simplest dark energy model, the cosmological constant with equation of state parameter equal to -1, and with general relativity. More exotic dark energy models and modified gravity theories face increasingly tight constraints. However, uncertainties remain significant, and improved measurements from upcoming galaxy surveys will substantially strengthen these tests. Future void-based dark energy studies will benefit from next-generation galaxy surveys that map billions of galaxies across cosmic time. Surveys like Euclid, The Vera Rubin Observatory's Legacy Survey of Space and Time and the Nancy Grace Roman Space Telescope will identify millions of voids with well-measured properties, enabling precision tests of dark energy and gravity that are impossible with current data. The connection between voids and dark energy illustrates how even the emptiest regions of space contribute to our understanding of fundamental physics. The voids, shaped by dark energy's influence on cosmic expansion and structure growth, carry in their properties information about one of the deepest mysteries in modern physics. By studying emptiness, we learn about the force that's pushing the universe apart, driving it toward an ever more dilute and isolated future. In science, some of the most interesting discoveries come not when observations match predictions perfectly, but when subtle discrepancies appear, tensions between theory and observation that might hint at new physics or reveal gaps in our understanding. One such tension that has emerged in recent years involves the abundance of cosmic voids, the number of voids of different sizes that we actually observe compared to the number that cosmological simulations predict. The standard cosmological model, called lambda CDM, combines general relativity with a cosmological constant, lambda, representing dark energy and cold dark matter, CDM. This model has been remarkably successful in explaining a vast range of observations, from the cosmic microwave background to galaxy clustering to supernovae distances. With just a handful of parameters, the Hubble constant, the densities of dark matter, dark energy, and ordinary matter, and a few others, lambda CDM predicts the evolution and properties of cosmic structure. Simulations based on lambda CDM can predict the abundance of structures of all types and sizes, including cosmic voids. By starting with initial conditions matching the observed cosmic microwave background and evolving billions of dark matter particles forward through cosmic time using the equations of gravity, these simulations produce synthetic universes that look remarkably like the real. From these simulated universes, researchers can identify voids using the same algorithms applied to real data and count how many voids of each size exist. When these predictions are compared to observations, interesting patterns emerge. In some galaxy surveys, the observed abundance of voids matches predictions quite well. But in others, particularly for certain void size ranges or in specific surveys, there appear to be systematic differences. Some studies find more large voids than predictions suggest should exist. Others find that void density contrasts differ slightly from simulated values. These discrepancies might not sound dramatic. We're often talking about differences of 10 to 30%. But in precision cosmology, such tensions deserve attention. They could arise from several sources: observational systematics, differences between simulation methods and reality, or, most intriguingly, hints that our cosmological model needs refinement. Observational systematics include all the ways that real galaxy surveys differ from idealized ones. Real surveys have boundaries that can artificially affect void identification. They miss faint galaxies that simulations would include. They have variations in depth and completeness across the surveyed region. Selection effects might cause certain types of galaxies to be included or excluded in ways that affect the identified void population. Accounting for all these effects requires careful work, using mock catalogs drawn from simulations to test how survey limitations affect void measurements. Even when observational effects are carefully modeled, some tensions persist. This raises the question of whether simulations accurately capture all the relevant physics. Most cosmological simulations follow only dark matter, adding the galaxy distribution afterward using empirical or semi-analytic methods. But real structure formation involves complex interactions between dark matter, gas, stars, and supermassive black holes. Feedback from supernovae and active galactic nuclei can push gas around, potentially affecting the distribution of galaxies without changing the underlying dark matter distribution much. Could these baryonic effects alter void properties in ways that aren't captured in dark matter-only simulations? Recent hydrodynamic simulations that include gas physics suggest the effects are generally small for large voids. As we expect, since voids are matter-poor and baryonic processes are most important where gas densities are high. But subtle effects might exist, particularly for smaller voids or in specific density regimes. More speculatively, the void abundance tension might hint at new physics. If the true nature of dark energy differs from a simple cosmological constant, this could affect structure growth rates in ways that alter void properties. If gravity behaves slightly differently on cosmic scales than general relativity predicts, void formation and evolution might proceed differently than standard simulations assume. If dark matter properties differ from the cold dark matter paradigm, perhaps dark matter is slightly warm or self-interacting, small-scale structure might be suppressed, potentially affecting void abundance. One specific scenario that's received attention is whether local observations of the Hubble constant, which seem to give a value about 5 to 10% higher than inferred from the cosmic microwave background, might somehow be related to void properties. If we happen to live in a region that's slightly underdense compared to the cosmic average, perhaps near or partly within a void, local expansion rates might differ from the global average. While most analysts suggest we're not in a void substantial enough to fully explain the Hubble tension, the possibility that a local environment affects measurements of expansion rates remains an active research area. Resolving the void abundance question requires improved data and better theoretical understanding. The next generation of galaxy surveys will map far larger volumes with more complete galaxy samples, enabling much more precise void catalogues. Upcoming simulations will include more sophisticated physics, particularly hydrodynamic simulations that follow gas and galaxies with high resolution. And new theoretical work will refine void-finding algorithms and develop better predictions for how baryonic effects and observational systematics affect void measurements. It's entirely possible that with improved data and modeling, the apparent void abundance tension will dissolve. We might find that once all effects are properly accounted for, observations and predictions agree within uncertainties. This would be a success for lambda CDM, confirming that the standard model works even for these subtle tests. Alternatively, the tension might strengthen with better data, suggesting that something in the standard picture needs revision. This would be exciting, potentially pointing toward new physics, modified dark energy, unexpected dark matter properties, or even more exotic possibilities like modifications to gravity or early universe physics that leave subtle imprints in late-time structure. The void abundance problem illustrates how cosmology has matured into a precision science. We're now sensitive to percent-level differences between theory and observation. We can test our models with structures as subtle as cosmic voids, using their statistical properties to constrain fundamental physics. And we have the theoretical tools and computational power to make detailed predictions that can be compared to observations in sophisticated ways. Whether the void abundance tension represents a true challenge to lambda CDM or a reflection of subtle systematics we haven't fully accounted for remains to be determined. But either way, the careful study of cosmic voids, their numbers, sizes, shapes, and evolution contributes to our understanding of cosmology and tests our standard model in ways that complement other cosmological probes. The voids, despite their emptiness, have much to teach us about the universe. Let us embark on a thought experiment, a journey through one of the great cosmic voids. Imagine we possess technology far beyond our current capabilities. A starship capable of traveling at a substantial fraction of light speed, sustainable for millions of years with an immortal or multi-generational crew. We depart from our galaxy, located in a relatively dense region of the cosmic web, and set our course toward the heart of a void, a voyage that will take us through the emptiest regions of the observable universe. At the beginning of our journey, as we leave the gravitational influence of our home galaxy, we can still look back and see it as a bright disk, its spiral arms traced out in the light of billions of stars. Around us, other galaxies of our local group remain visible, familiar signposts in the cosmic landscape. The nearest large cluster of galaxies glows in the distance, its thousands of galaxies forming a concentration of light marking where the cosmic web grows dense. We travel for 1 million years at, say, half the speed of light. We've now covered 500,000 light years, more than enough to leave our galaxy's immediate neighborhood. Looking back, our home galaxy has diminished to a bright point, distinguishable from foreground stars only by its steady, unchanging light and its position at the calculated location. Around us, space seems darker. The density of background galaxies in our field of view has begun to decrease as we approach the edge of the filament that contained our starting point. After 10 million years of travel, we've covered 5 million light years. We're now crossing into underdense regions. The number of bright galaxies we can see has decreased substantially. Those that remain visible tend to be small, blue systems, the typical void galaxy population we discussed earlier. The great galaxy clusters that dominated our initial view have receded into the distance, their light faint and reddened by cosmological redshift. At 50 million years into our journey, having traveled 25 million light years, we are deep in the void. If we could map the galaxy distribution around us, we'd see that we're in a region with perhaps 20% of the average cosmic density. The nearest substantial galaxy might be 10 million light years away, a faint smudge requiring our instruments to detect. If we look in any direction, the void extends away from us, with the nearest filaments and walls of the cosmic web forming distant boundaries to this empty realm. The sky has changed dramatically from our departure. Looking back toward our origin, the filament we left behind appears as a concentration of faint galaxies, a thin line or sheet of light against the general darkness. Perpendicular to this direction, in the directions that lead deeper into the void, we see almost nothing. Occasional faint galaxies scattered at vast distances, but mostly just the background cosmic microwave radiation and the integrated glow of all distant galaxies blended into a faint, diffuse luminosity. What would we actually observe during this journey? The cosmic microwave background remains detectable, its temperature still 2.7 Kelvin, modified slightly by our motion through space, producing a dipole pattern where we're moving toward a slightly warmer direction and away from a slightly cooler one. The extragalactic background light, the integrated glow of all galaxies, is fainter than in denser regions, simply because fewer galaxies contribute to it from our current location. Occasionally, we'd detect high-energy cosmic ray particles passing through our vicinity. These particles, accelerated by distant astrophysical processes, traverse the void unimpeded by the sparse matter. We might detect neutrinos from distant supernovae or from the cosmic neutrino background. Rarely, we might observe a gravitational wave signal from merging black holes or neutron stars in distant galaxies, the ripples in space-time reaching us after crossing void and filament alike. The intergalactic medium through which we're traveling is extraordinarily thin, perhaps 10 to 100 hydrogen atoms per cubic meter. If our ship has a cross-section of 1,000 square meters and travels at half light speed, we'd sweep through roughly 100 million cubic meters per second, encountering about 1 billion to 10 billion atoms per second. This is enough that over millions of years, we'd need to account for drag and erosion from these rare collisions, even though the medium is far more tenuous than any vacuum achievable on Earth. As we continue deeper into the void, traveling for 100 million years, 200 million years, we'd observe that the void has no distinct center. It's not a spherical bubble with a definite boundary. Rather, it's a complex, irregular region with tendrils, substructure, and variations in density. Sometimes we'd pass through regions slightly denser than the surrounding void, perhaps containing a small group of dwarf galaxies. Other times we'd cross through even emptier regions, with no galaxies detectable for tens of millions of light-years in any direction. The psychological impact of this journey on our crew, assuming humans or human-descended beings, would be profound. For millions of years, the travelers would see a universe that appears almost empty, with only the faintest evidence of structure beyond their immediate vessel. The rich cosmic tapestry visible from Earth, with thousands of galaxies visible through telescopes and nebulae, painting the Milky Way across our sky, would be replaced by near total darkness, punctuated by rare, faint smudges of light. Yet they would not be truly isolated. Radio signals from distant civilizations in galaxies throughout the cosmic web might still reach them, though communication delays of tens of millions of years would make dialogue impossible. Light from distant quasars and galaxies would continue arriving, carrying information about cosmic structure and evolution. The travelers would remain part of the universe, participants in its expansion, observers of its contents, even in this emptiest of regions. After perhaps 300 million years, having crossed 150 million light-years, our ship would approach the far side of the void, entering the transition region where galaxy density begins to increase. The number of detectable galaxies would grow. The integrated background light would brighten. Eventually, we'd enter a filament on the far side, seeing galaxy density return to average levels and eventually exceed them as we approached a galaxy cluster. This journey illustrates the scales of cosmic voids and the profound emptiness they represent. A civilization confined to a single galaxy, even with technology allowing travel at substantial fractions of light speed, would find voids to be nearly insurmountable obstacles, requiring voyages lasting longer than most civilizations might persist. The voids are empty not just in space, but in time. Crossing them means crossing epochs, geological age, evolutionary timescales. And yet, throughout this journey, we'd remain in the same universe, under the same physical laws, observing the same cosmic microwave background, watching the same cosmic expansion. The void is part of the same cosmic web as everything else, just the negative space within that web, the emptiness that gives structure to the whole. Cosmic voids are not static structures frozen in their current state. They evolve over cosmic time, changing in size, depth, and properties as the universe ages and expands. Understanding how voids evolve means understanding the interplay between gravitational structure growth and cosmic expansion, processes that together determine the fate of cosmic structure over billions and trillions of years. In the early universe, shortly after the formation of the cosmic microwave background, structure was just beginning to grow from tiny primordial fluctuations. At that epoch, about 380,000 years after the Big Bang, the density variations were only about 1 part in 100,000, minuscule differences that would require billions of years of gravitational amplification to become the cosmic web we observe today. At that early time, you couldn't meaningfully identify voids yet. The universe was nearly homogeneous on large scales, with only the seeds of future structure present. As the universe aged and expanded, those tiny fluctuations grew under gravity's influence. Overdense regions attracted more matter. Becoming denser to dense, regions lost matter to their neighbors, becoming emptier. By about 1 billion years after the Big Bang, clear structures were emerging. The first galaxies were forming in the densest regions, and under-dense regions were beginning to develop into recognizable voids. The formation of voids accelerated as structure grew. Matter flowed along gravitational potential gradients, channeling from underdense regions into filaments and nodes. By 3 to 5 billion years after the Big Bang, the cosmic web's basic structure was established, with clear filaments, walls, and voids. However, this structure continued to evolve, with voids growing larger and emptier as more matter evacuated them. During the first several billion years, the growth of cosmic structure was slowed by the fact that the universe was matter-dominated. The gravitational attraction of matter was working against the cosmic expansion to slow it down. While expansion carried things apart, gravity pulled them together, and the balance between these forces determined how quickly structure could grow. But about 5 to 6 billion years ago, dark energy began to dominate the universe's energy budget, causing cosmic expansion to accelerate. This transition had profound effects on structure formation. Accelerated expansion works more strongly against gravitational attraction, slowing the growth of structure. Voids, which had been steadily growing and deepening, found their growth rate affected by the onset of acceleration. In an accelerating universe, the growth of structure, including the growth of voids, proceeds more slowly than it would in a matter-dominated universe. Dense structures like galaxy clusters continue to grow by accreting matter from their surroundings, but this process slows down. New clusters become rarer as time goes on. Similarly, voids continue to grow and empty out, but more gradually than before. The current epoch, about 13.8 billion years after the Big Bang, finds cosmic structure in a transition period. The structures we observe today, the galaxy clusters, filaments, and voids, will continue to evolve, but increasingly slowly as dark energy's influence strengthens with ongoing expansion. New voids will form from currently underdense regions that aren't yet empty enough to qualify as true voids, but the growth of existing voids will gradually slow. Looking toward the future, we can use cosmological models to predict how voids will evolve over the next billions and trillions of years. In the standard lambda CDM model, where dark energy takes the form of a cosmological constant with equation of state parameter equal to -1, cosmic acceleration continues indefinitely. The expansion rate approaches a constant value, and the universe enters a phase called the de Sitter era, named after the mathematician Willem de Sitter, who studied such spacetimes. In this far future, structure growth effectively freezes. The gravitationally bound structures, individual galaxies and galaxy clusters, remain bound, held together by their own gravity despite cosmic expansion. But the spaces between these structures expand ever more. Voids grow larger as expansion carries their bounding filaments and walls farther apart. The galaxy density within voids, already extremely low, decreases further as the few galaxies present recede from each other. By 100 billion years in the future, the universe will be significantly larger and emptier than today. Voids will have grown by a factor of several, and the overall galaxy density in voids will have decreased proportionally. The sparse galaxies within voids will be even more isolated, with typical separations growing from tens of millions of light-years today to hundreds of millions of light-years. In this distant future, an observer in a void galaxy would see an even emptier cosmos than void dwellers see today. The nearest other galaxy might be invisible even to powerful telescopes, its light so redshifted by the intervening expansion that it falls into the infrared or beyond. The cosmic web structure, filaments and clusters, would have largely disappeared from view, with most galaxies beyond the cosmological horizon, the distance beyond which recession velocities exceed light speed. The cosmic microwave background would still be detectable but colder, its temperature reduced by continued expansion. The current 2.7 Kelvin would have cooled to perhaps 0.3 Kelvin in 100 billion years, and lower still beyond that. The universe would be darker, colder, and emptier than at any previous epoch. By 1 trillion years in the future, assuming dark energy remains a cosmological constant, the universe will have entered its lonely endgame. Most galaxies will be beyond the cosmological horizon, their light unable to reach us as the space between expands faster than light can cross it. Each galaxy or galaxy cluster becomes its own isolated island universe, causally disconnected from all others. Voids will separate these island universes, growing ever larger as expansion continues. The few stars still burning in this far future will be low-mass red dwarfs, the longest-lived stellar type, slowly consuming their hydrogen over tens of trillions of years. Star formation will have largely ceased throughout the universe as gas supplies are exhausted and not replenished. Galaxies will darken as their stars age and die, with fewer and fewer new stars forming to replace them. In this era, the voids will be truly dark and empty. The sparse galaxies they once contained will have exhausted their gas and ceased forming stars. The intergalactic medium will have cooled and thinned further. The magnetic fields, already weak, will have diluted to near nothingness. Only the dark matter, the cosmic microwave background photons, and the occasional gravitational wave will remain as evidence that the universe contains anything beyond empty space. Yet even this is not the end of void evolution. If we project forward to truly extreme timescales, 10 to the power of 100 years or beyond, even more exotic processes come into play. Protons might decay, if certain theories of particle physics are correct, causing all ordinary matter to gradually disintegrate into lighter particles and radiation. Black holes will evaporate through Hawking radiation, a process that takes 10 to the power of 67 years for a solar mass black hole, and much longer for supermassive black holes. In this ultimate era, the universe, and the voids within it, will consist essentially of nothing but extremely dilute radiation and whatever stable particles remain. The temperature will approach absolute zero. The expansion will have carried structures so far apart that causally connected regions will be vanishingly small compared to the universe as a whole. Each observer would see essentially nothing but their own local region, with the rest of existence beyond any possible contact. The voids, in this final state, will be indistinguishable from any other region. The distinction between void and filament, which arose from small primordial fluctuations and was amplified by gravity over billions of years, will have faded. Everything will be equally empty, equally cold, equally dark. The universe will have become, in effect, a single vast void. This far future evolution of voids reminds us that the structures we see today, galaxies, clusters, filaments, and voids, are temporary arrangements of matter, temporary features of a universe in transition from its hot, dense beginning to its cold, empty future. The voids represent the future toward which everything is heading, a preview of the universal emptiness that awaits when expansion has carried all structures beyond reach and time has exhausted all energy sources. Yet from another perspective, the evolution of voids is a story of structure and pattern persisting for vast stretches of time. For tens of billions of years into the future, the cosmic web will remain recognizable. Voids will exist as distinct structures, different from filaments and clusters. The universe will maintain organization and complexity, even as it gradually trends toward uniformity. Understanding void evolution helps us place our current epoch in cosmic context. We live in a special time, when the universe is old enough for rich structure to have formed, but young enough that this structure remains visible and dynamic. The voids around us are not static features, but evolving structures, growing and changing, products of cosmic history and participants in cosmic future. They connect the early universe, with its tiny fluctuations, to the far future, with its ultimate emptiness, serving as one thread in the vast tapestry of cosmic evolution. As we approach the end of our journey through the cosmic voids tonight, here on Whispering Universes, let us pause to contemplate what we've learned about these vast, empty regions and what they mean for our understanding of the cosmos and our place within it. The voids are, in the most literal sense, the largest structures in the observable universe. They occupy more volume than all other cosmic structures combined. They define the shape of the cosmic web as much as the filaments and clusters do, perhaps more so, as the web is fundamentally a network of walls surrounding empty spaces. Without the voids, there would be no cosmic web, just as without the air spaces, there would be no foam. We've learned that these voids are not truly empty. They contain dark matter, though at low density. They contain diffuse gas heated to millions of degrees, carrying most of the ordinary matter in these regions. They're threaded by weak magnetic fields, crossed by radiation from every corner of the universe, and home to sparse populations of small, blue, actively star-forming galaxies. They're pervaded by the cosmic microwave background, that ancient light from the universe's beginning, carrying imprints of the void's gravitational potential. The voids formed through the same gravitational process that created all cosmic structure, growing from tiny primordial fluctuations into vast underdensities as matter evacuated them over billions of years. They continue to evolve today, growing larger and emptier as cosmic expansion proceeds and dark energy accelerates the universe's expansion. In the distant future, they'll grow larger still, separating structures by distances that dwarf even their current enormous scales. We've seen how voids serve as laboratories for fundamental physics. Their properties test our understanding of dark energy, that mysterious component causing cosmic acceleration. Their abundance and evolution constrain cosmological models and might reveal hints of new physics beyond the standard paradigm. Their effects on the cosmic microwave background provide independent evidence for dark energy's existence and properties. Their emptiness makes them ideal places to study the intergalactic medium, magnetic fields, and other subtle phenomena that are complicated by high densities elsewhere. The voids raise profound questions about perspective and context. If intelligent life exists in void galaxies, and statistically, it probably does somewhere, those beings would perceive a fundamentally lonelier cosmos than we do. Their nearest galactic neighbors would be tens of millions of light-years distant rather than millions. Their night sky would be darker, emptier, more mysterious. Their path to understanding cosmic structure would be more difficult, requiring deeper observations and more sophisticated analysis. Yet those void dwellers would ultimately discover the same universe we inhabit. They'd measure the same cosmic expansion, detect the same cosmic microwave background, infer the same dark matter and dark energy. The physical laws they'd uncover would be identical to ours. Their mathematics would describe the same geometric truths. They'd be part of the same cosmos, just viewing it from a different, lonelier vantage point. The voids also invite us to contemplate emptiness itself, what it means for space to contain almost nothing, and whether such emptiness is merely an absence or something more. In physics, the quantum vacuum is not truly empty, but seethes with virtual particles and zero-point energy. The vacuum of space contains fields, gravitational, electromagnetic, perhaps others we haven't discovered, that permeate all regions. Even the deepest void is not nothing. It's space itself, that most fundamental arena where existence plays out. There's a kind of poetry in the voids, a beauty in their emptiness that complements the beauty of stars and galaxies. They're the silence between the notes in cosmic music, the blank canvas that makes the painted regions meaningful. They provide context and contrast, making the rich structures elsewhere seem richer by comparison. They remind us that structure requires both presence and absence, density and underdensity, matter and void. As cosmologists continue mapping the universe with ever greater precision, the voids will become even better known. Future surveys will identify millions of voids, measuring their properties with unprecedented accuracy. Simulations will predict their characteristics with increasing fidelity. The subtle tensions between observation and prediction may resolve, or they may sharpen into clear evidence of new physics. Either outcome will advance our understanding. In the deep future, long after human civilization as we know it has transformed or ended, the voids will continue their slow evolution. They'll grow larger as the universe expands. They'll become emptier as matter disperses. Eventually, on timescales that dwarf the current age of the universe many times over, the distinction between void and non-void will fade as everything approaches uniform emptiness. The universe will have become, in essence, a single vast void, cold and dark and nearly empty, with the last remnants of structure, isolated black holes perhaps, slowly evaporating, scattered across distances beyond any possibility of interaction. But that far future remains almost unimaginably distant. For now, and for billions of years to come, the voids will persist as distinct structures within the cosmic web. They'll continue to tell us about dark energy, structure formation, and the nature of space itself. They'll serve as reminders of scale, that the universe is vastly larger and emptier than our everyday experience suggests, that the distances between things can be as important as the things themselves. For us here on Earth, residing in a relatively dense region of the cosmic web, near several large galaxies, and within sight of rich galaxy clusters, the voids are distant features, observable through our telescopes, but not part of our immediate neighborhood. Yet they surround us. They define the structure within which we're embedded. They participate in the same cosmic evolution that shapes our local environment. We're connected to them through gravity, through the cosmic expansion, through the shared history stretching back to the Big Bang. As you drift toward sleep tonight, imagine floating in the center of a cosmic void. The darkness around you is nearly complete, broken only by the faintest smudges of distant galaxy light at the edges of vision. The silence is profound. No stellar winds, no supernova shockwaves, no radiation from nearby objects to disturb the quiet. You're surrounded by space in its most minimal form, the closest the universe comes to nothingness, while still being something. And yet, even here in this deepest darkness, you're not alone. The cosmic microwave background photons surround you, having traveled for nearly 14 billion years from the moment of the universe's birth. Dark matter particles pass through your position, invisible but present, their gravity weak but real. Neutrinos stream by at nearly light speed, messengers from distant stars and from the Big Bang itself. The vacuum of space seethes with quantum fluctuations, temporary violations of energy conservation that create and annihilate particle pairs too quickly to detect directly. You're floating in emptiness, but it's an emptiness that's part of the whole, connected to everything else, shaped by the same force and following the same laws that govern the richest galaxy clusters. The void is not separate from the cosmos, but integral to it. The emptiness gives meaning to the fullness. The silence gives meaning to the sound. The darkness gives meaning to the light. Let your consciousness drift now, like a photon crossing this vast empty space, free and unbounded. Let the boundaries between presence and absence soften in your awareness. The void is not something to fear, but something to contemplate. A reminder of the universe's vastness, its variety, its capacity to contain both everything and almost nothing. Thank you for joining this exploration here on Whispering Universes. If you've enjoyed this journey through the cosmic voids, please consider liking and subscribing for more explorations of the cosmos and its mysteries. Until next time, rest well in the knowledge that even the universe's emptiest regions contain wonders waiting to be understood. Sleep peacefully, dream deeply, and remember that even in the deepest darkness, you are part of something larger. This vast, evolving, magnificent cosmos that contains both galaxies and voids, both matter and space, both structure and emptiness, all woven together into the grand tapestry of existence. Let the gentle darkness of the cosmic voids carry you now toward sleep, toward dreams, toward rest. The universe continues its patient expansion. The voids grow slowly larger, and everything evolves according to natural law toward whatever future awaits. For now, there is only this moment, this breath, this drift toward peaceful sleep under the same cosmos that contains both everything and nothing at all. Good night from Whispering Universes.